presentation which I'm going to talk about today is related to the validation of the software SAFIR. I'm a user of the SAFIR software. I'm using it since 2013. And as Jeremy presented before, I think in various countries there are different rules, and in some cases the authorities can ask for validation exercises when the users are using advanced thermal or structural analysis. The presentation is tailored around SAFIR software, but the principles of the presentation and the idea behind the presentation, you can use it with any sort of advanced finite element analysis software. What we'll go through today is a collection of examples. It's a collection of validation studies, which I've done during the years. And we will look at different forms of construction. We will look at thermal analysis, structural analysis. We have, in this case over here on the right-hand side in this image, we've got an example of a cavity barrier, and with an aluminium mullion, which is penetrating the cavity barrier. It's a very common question on the UK consultancy market. In terms of fire resistance testing and numerical modeling, this is one of my favorite slides, actually. We've got an example over here of a universal column, which is 203 by 203 by 52 kilograms, and this is a hybrid encasement. And the idea, what we'll go through the presentation, we'll look at standard fire resistance testing and data, and then we'll look at the possibilities to model the boundary conditions in the standard fire resistance test data, and then to look at various materials and different material properties and things like that. For example, over here, we can see in this prediction, we can see in this graph the prediction and the analysis, which we'll see over and over through various forms of construction. And then in some cases, you can run your structural analysis if this is the idea of that specific application, or you can just look at the thermal model. We can see in this case specifically that we've got a 99 minutes fire resistance load bearing capacity from the furnace test, and then we've got 95 minutes from SAFIR, which is absolutely brilliant. And this is what we are going to look throughout the presentation today. Obviously, we've got some advantages and disadvantages in terms of fire testing and numerical modeling. We can't do numerical modeling without fire testing. I think this is the most important aspect, but we can do fire testing without numerical modeling. However, we've got a lot of advantages in numerical modeling, especially in terms of extrapolation. So you can use different variations, in this case of the column, in other cases of other elements, and then you can extrapolate your data, and you can save a lot of time and a lot of money, basically, on standard fire resistance fire testing. And in some cases, it's impossible to apply standard fire resistance testing, and we'll look at this. What I would recommend in terms of references, I would recommend these two books, which are really good. The first one on the left-hand side has a collection of standard fire resistance tests done over here in the UK in 1950s, which is looking at forms of construction around about 1900. And then the second one, it was published in 1988, and it gives tabulated data for various forms of construction. This is very useful, specifically for the users today which are involved in commercial applications. And we'll go through different examples, and we've got lath and plaster ceilings. These ceilings are unique, I would say, from my perspective. They are very well established over here in the UK, especially for buildings in 1900, 1920s. We can see in the picture that's a listed ceiling in a listed building. So as you can imagine, it's very difficult to test under standard fire resistance conditions these types of ceilings. And we've got an example which is timber lath and plaster, and we've got another example which is metal lath and plaster, which is actually slightly better because of the support construction. And we can see obviously in the drawing some of the details of the general construction details. And what we did, I mean, the first question is, how would we determine the standard fire resistance? Well, the anticipated fire resistance for such a form of construction. And we can look at tabulated data, which I gave you the references. We can do standard fire resistance testing, or we can do advanced analysis. I mean, the first port of call would be to look at if there is any data available in terms of tabulated data. So what you can see over here in this document, which is BR128, it's a very good document. You can see that the 15 millimeters of timber lath and plaster would give you around about half an hour. And then a 19-20 mil of expanded metal lath and plaster will give you around about 60 minutes. And in order to check the tabulated data and to add another layer of assurance, or in case if your lath and plaster layer is different than what you can find in the tabulated data, we said let's have a look on what sort of fire resistance data we have for this form of construction. And we found some tests done many decades ago, which are on timber floors. Yeah, so this is a section through the floor system. I won't go into the modeling details. Obviously, these are cavities, open cavities, timber floor joists with the timber lath and plaster 20 mil thick at the bottom and a timber cover on the top. And then we can see over here the temperature distribution at 60 minutes. And for this specific application, we've developed user-defined thermal properties for the lath and plaster layer. And then we validated these user-defined thermal properties against the test data, what you can see on the right-hand side. So what you can see, the blue points over here are points measured during the standard fire resistance test. And then the line obviously is the prediction from the numerical model. And the blue points are on the top side of the lath and plaster layer, and then the other points are on the unexposed face of the system, which is really good, I think, in terms of comparison. And this sort of details will go through each and every individual form of construction. Okay, and we move on. We have other examples on protected steel members. Obviously over here columns, and we've got beams. What you can see on the pictures below is me when I was younger, measuring the cover to the column and cover to the beams. In the same idea, we determined the fire resistance, anticipated fire resistance through the same steps. So in the first step, we can look at tabulated data. Again, in BR128, I think you can find something like this in the Eurocodes as well. Some of them, they provide tabulated data for various forms of construction. You can see for solid protection, you've got the cover to your steel member, and then that gives you the anticipated fire resistance. And if you want to do, if the user wants to change anything in that specific, or the cover is different, we've got again over here standard fire resistance test data for a steel encased column in concrete. We've got all the details in terms of moisture, duration, compression, resistance, and cover. We've done our numerical thermal heat transfer model, and we can see a very good correlation. And then if you run your structural model, you can see the results over here. We've got from the test 181 minutes, 183 minutes from the advanced numerical analysis, and then 120 minutes from the tabulated data. So if you want to go beyond the analysis, the tabulated values, then you can look at this. And then this is another interesting project, which is standard fire resistance test data for plasterboards, plasterboard encased column, yeah, which is a really interesting project. Hopefully we'll publish something soon. So what we are looking is to define a user-defined material properties for generic type of plasterboard, which is type F. So what you can see over here is the three different tests on the 205 by 205 by 52 steel column. The first three tests are with one layer of 15 mil plasterboard. The second test are two layers of 15 mil plasterboard, three different manufacturers. Yeah, so three different solutions. And then we are looking to, so we did a lot of testing. This is a column furnace, which is unique in Europe, our column furnace. I think there is one in Liège as well, and maybe one in Effectis. This is a 500-ton, compressive machine for the column furnace. So we did the testing, for the 6 columns, different protections, as I mentioned. So we can see first test over here, second one over here. We can look at the failure mechanism. In some cases, we have fall off of the plasterboard. In some cases, local buckling, global buckling, all sorts of failure mechanisms for the columns presented below. And then we move on and we did some numerical analysis and obviously the validation for this specific column. So what we can see on the two graphs on the left hand side is the one layer protection, two layers protection on the right hand side. And we can see with the red dotted line over there the prediction from the numerical model and in comparison with what was measured in the standard fire exposure, which is really good. And then if you do your structural analysis, what you'll find out is that you get 69 minutes, for the one layer of plasterboard and 125 minutes straight on, exactly like in the test results. However, I have to mention over here that the thermal properties for plasterboard, for columns specifically, are slightly different than the one used for the walls. Because it's a completely different forms of construction. So we did some adaptations of these thermal properties, and this is one of the advantages of SAFIR, because it lets you to define your own thermal properties for whatever materials you are using. And then we move on, steel member passing through compartment walls. This is the tests over here, which we can see in the image, have been done at VTT in Finland, and it's a big question over here in the UK of unprotected members passing through compartment walls. This is the sample arrangement. They did some testing, and we're looking, based on their data, we're looking to see if SAFIR is able to predict something like this. And this is a 3D temperature distribution map. We can see over here our concrete block. We can see the steel member passing through. And then if you look at the temperature history comparison, this looks great. It's almost looks like it's made up, but it's not. Okay, and we move on. Reinforced concrete columns. This is very well established in terms of type of form of construction which SAFIR can deal very well with. There are a multitude of papers on in journals and in literature. You can find and read more. This is just an example. We look at a reinforced concrete column, and then we've got the dimensions over here in terms of, and all the data in terms of cover, load ratio, diameters, and all sorts of longitudinal reinforcement ratio and things like that. And then we move on and we do our numerical analysis. So in the first instance, you have to perform the heat transfer analysis. And then we look on the right-hand side, we can see obviously what was measured and what was calculated. So very good results. In terms of material properties, we do our structural model, and then from the structural model we get our fire resistance. What you can see in this graph over here, actually the yellow dot is what was measured during the test. The test ran for 120 minutes. It's a null test, and they just wanted to see if the column is able to provide 120 minutes. They didn't want to failure. However, what you can see over here is that from the tabulated data, you get 120 minutes, 500 degrees isotherm in the Eurocode. You play a little bit with it, you get 120 minutes, you have 10% reserve capacity, and then in your numerical analysis, you get 120 minutes. So if you always want to go beyond the simplifications in the tabulated data or simplified methods, advanced numerical modeling is an option. And then I'm going to discuss a little bit on historic floors. So some of these you may have seen at Structures in Fire conference in Portugal. I won't go in too much detail. If you want to read more about it, there is a paper in the proceedings. Please access that. It's a very old form of construction used over here in the UK. We've got a couple of examples in the images, and then we've used existing tests. Yeah, so we have a database of tests that you can see over here. This is a prediction of the temperature distribution on lower flange and upper flange, and we can see quite a good prediction. And then you can obviously play and do a 3D structural model. We did actually 2D, but initially we went on 3D structural model. It's a bit more complicated, but what you can get your deflection data in comparison with what the test had. So it's quite similar, I think. And yeah, it can be used just using the material properties provided in the guidance such as Eurocode. And then hollow pot floor, this is again another form of construction used in the UK in 1900s, 1920s. And then I think the title over here, it's yeah, it should say hollow pod floors, but that's fine. We look the same thing. We have a heat transfer model on the section of our floor. We've validated this through a series of tests. You can see some of them are under predicted over here. This is because of spalling, but most of them, this is the temperature of the reinforcement, as we can see over here, where the reinforcement is positioned inside the floor. And then if you run your structural analysis, you get very good results. For instance, you get 200 minutes load bearing capacity from the test, 204 minutes from SAFIR. This is really good, actually. And then we carry on, we move on. This is a more unusual, I would say, application of SAFIR. This is fire stopping, yeah. So we're looking to fire stopping solutions into curtain wall systems. This is a simplification of the heat transfer model. This is our fire stopping in the middle. These are other materials around the fire stopping. And then we can obviously see over here a lot of data plotted from the test. And we can see with the correct material properties a very good result from the thermal modeling of SAFIR. Again, more examples. This is an example of lye steel frame solutions. There are a lot of papers and a lot of data for lye steel frame solution. What I would recommend to users, it's the plasterboard. It's complicated to model it. It has a complex behavior in fire. I would recommend when you do analysis on them for commercial work, just work on test evidence. So you need to get a test report first, and then you can expand your analysis based on that. So you can look at fall off time and things like that. This is an example of a 60-minute solution. We can see on the right hand side the temperature history comparison, very good, super happy with these results. And then on the just below that 120-minute solution, again, absolutely superb results, I would say, from the software. If you use the correct material properties, this is a non-load bearing solution. You can obviously get your temperature distribution on the studs. You can use the Euro codes to calculate your class 4 section capacity, and you can do a lot of stuff, actually. I'm not sure if you can actually model the stud in SAFIR, but I haven't tried it. This is another example. This is, part of other applications of the software. This is a stone column construction detail. This is an isometric view. The question over here, this stone column has a rubber bearing. So the question was, in a standard fire, how would this rubber bearing perform? And we are going to do some tests on this column. This is just the preliminary analysis on the column. And then we'll have a look on the numerical model. This is the general boundary conditions. We can see a symmetry axis. We've just modeled half of the column. This is the model over here on the left-hand side. It's quite complex. This is in GM SAFIR, the 2022 version, which from my point of view is much better, especially for 3D analysis than the previous preprocessor, which was JID. I always had issues with the JIT software, but this is much more flexible. You can build very complex models in 3D. What the post-processor allows you is to isolate each and every component. So you can see over here, this is the rubber bearing, this is the insulation in the bearing in different planes. You've got stainless steel dowels, you've got grout, all sorts of materials. You can use different material properties for different layers. And then you get your results, which they look quite nice. You can isolate components. You can look at temperature distribution in 3D and all sorts of values. And in terms of conclusions, I mean, there are a lot of things to say. I think SAFIR, it's a very good software. Jeremy mentioned the previous, it's a very well-established software. You can always learn something new. Such as me, today I didn't know about the GoZone project. And then you can read the conclusions. I mean, one of the most important things is that the results of the numerical model are user dependent, are material dependent, but user dependent as well. So the user, they have to be very careful what sort of data they use and how they calibrate their model to get their confidence into the results. This is another example over here on the right hand side. This is a more complex model, is a steel beam. It's a connection between an unprotected and a protected steel beam member. So you can do a lot of stuff, especially in 3D. And yes, thank you very much. And if there are any questions, I'm happy to answer.